Hi, I'm Eugene So from Digist, and I'm going to illustrate post-quantum cryptography migration on V2X certificate using KpqC algorithms. First, I want to tell some background. First background is PQC and KpqC. PQC is post-quantum cryptography, and KpqC is Korea post-quantum cryptography. PQC comprises cryptographic algorithms explicitly designed to resist quantum computer attacks. Recognizing the urgency of quantum-resistant cryptography, the National Institute of Standards and Technology NIST initiated a PQC standardization project in 2017. Similarly, Korea independently selected 4 algorithms conforming to national representative PQC algorithms in 2025. And next, digital signature algorithms. Digital signature algorithms ensures message integrity, authenticity, and non-repudiation by leveraging mathematical principles. This algorithm generates a signature using a private key and verifies it with a public key to confirm the authenticity and integrity of the message. Representative traditional signature algorithms include RSA and ECDSA. Specifically, the primary PQC signature algorithm selected by NIST is Crystal's Delicium, while Korea's primary PQC signature algorithm is Hate. And the Crystal's Delicium became the standardization of MLDSA. So MLDSA is based on Crystal's Delicium digital signature algorithms. Both algorithms fall under lattice-based cryptography. And finally, digital certificate. A digital certificate is an electronic document used to identify an entity, establish the owner's identity, and provide the owner or subject with a public key. Specifically, X.509 certificate generates a certificate in the data section, including X.509 version, serial number, algorithm information, issuer distinguished name, expiration date, subject distinguished name, and subject public key information. The signature section contains the encryption algorithm, the algorithm used by the issuer to generate the digital signature and digital signatures of the certificate authentication, CA. This value is the hash of all information in the certificate, encrypted with the private key. Second, the part of overview at our analysis. This study analyzes the impact of post-quantum cryptography algorithms such as Hate and MLDSA on the certificate of the TLS protocol for V2X applications. And we know TLS protocol is transport layer security protocol, and V2X is equal to everything. And there are many digital signature algorithms, not only Hate MLDSA, but also on other things. But I choose HATE and MLDSA. Our framework evaluates the effect of traditional and post-quantum cryptographic signature algorithms on certificate size, impacting the number of Ethernet packets required for transmission. This modular approach facilitates comparative analysis, highlighting implications for packet fragmentation and transmission delay in V2X scenarios. And next, required MTUs depending on each certificate sizes. So you can see the table 2. The table 2 details the certificate generation output for each algorithm. The core idea behind our implementation is to analogize the certificate size resulting from a standardized X.509 certificate generation process. As detailed in Table 2, the certificate sizes for traditional public key algorithms are significantly smaller than those KpqC algorithms. The traditional public key algorithms is RSA SHA-256 and ECDSA SHA-256. For instance, RSA SHA-256 and ECDSA SHA-256 produce certificates of 891 and 495 bytes respectively, sizes that easily fit within a single Ethernet transmission packet with a standard MTU of 1,500 bytes. And you can see the below box. A single Ethernet packet is 1 MTU equals 1,500 bytes. And MTU means maximum transmission unit. So a single packet at Ethernet, the size is 1,500 bytes. And by the way, in contrast, KpqC schemes yield substantially larger certificates. I mean, compared to traditional cryptographic certificate size. Specifically, the MLDSA variants have certificate sizes of 4,097, 5,626, and 7,584 bytes for MLDSA 44, MLDSA 55, and MLDSA 66, respectively, while the HATE implementations yield sizes of 2,813, 4,168, and 5,375 bytes for HATE 120, HATE 180, and HATE 260. Again, given that an Ethernet packet can carry a maximum of 1,500 bytes, certificates exceeding this size must be fragmented across multiple packets. This fragmentation naturally increases the number of packets required for a complete transmission. While both MLDSA and HATE certificates exceed the 1 MTU limit, Figure 1 shows that HATE certificates remain consistently smaller than their MLDSA counterparts for a given security level. Even we can see the number of packets at the lowest level of HATE. HATE 120 is smaller than the lowest level of MLDSA 44. So you can see the comparison of each algorithms at Figure 1. This reduction in required transmission packets is of particular importance in V2X communications where low latency is critical. In V2X scenarios, any increase in transmission delay, such as that introduced by packet fragmentation and reassembly, can negatively impact system performance and safety. Therefore, the smaller certificate sizes offered by HATE not only lower the overhead in TRS handshakes, but also present a significant advantage for delay-sensitive V2X applications, potentially leading to improved reliability and responsiveness in vehicular communication networks. So finally, our conclusion. Although the size of certificate with PQC schemes, both MLDSA and HATE exceed the 1 MTU limit compared to the size of certificate with traditional schemes. HATE certificates consistently remain smaller than their MLDSA counterparts for a given security level. Therefore, our findings suggest that within the post-quantum category, HATE offers a more favorable trade-off between security and transmission efficiency than MLDSA. We set the stage for the future optimization of TRS performance in the emerging post-quantum era. We provide a foundation for subsequent research incorporating additional signature algorithms and key encapsulation mechanisms, CAMs, and also there is a hybrid key encapsulation mechanism. So not only for whole key encapsulation mechanisms, but also we can choose some hybrid CAMs. We can evaluate their impact on security and performance in practical TRS environments. And also, we can check at V2X scenarios. Thank you.